Our second speaker this afternoon is Konstantin Ardakov. Konstantin was an undergraduate at the University of Oxford before going to Cambridge for his PhD, where, like me, he received his PhD under the supervision of Chris Brooks in 2004. Since then, he's had positions at Sheffield and Nottingham and Queen Mary in London, and he returned to Oxford about a year ago, where he now has a lectureship there. And he's going to speak on joint work with me on D modules on rigid analytic spaces.
Thanks very much, Simon. So it's a great honour to be here. Thank the organising committee for inviting me to speak here. So the title of my talk is Dhat modules on rigid analytic spaces. So what I'll do first is I'll explain and recall the basic theory of rigid analytic spaces. This is some kind of p-adic geometry. And then I'll talk about Dhat modules, what they are. And then I'll talk about some applications to representation theory of p-adic groups, which is really where this work came from. So non-Archimedean geometry, p-adic geometry. So P will be an odd prime, odd because P equals 2 causes all sorts of problems. So we'll work over some p-adic field K. You might as well assume it's contained inside the p-adic complex numbers. And we want to do some kind of geometry over this ground field K. So we want to look at spaces which are glued together out of small open subsets of affine space, maybe, over K. Just like you do in real geometry. Well, you encounter an immediate problem. Topologically, this is not a good thing to do because of the ultrametric inequality that holds inside the ground field K. If you look at the closed unit disk, that should be some kind of manifold. Well, obviously it's got an open subset, and because of the strong triangle inequality, actually this is also kind of open inside the plane, and the rim is also open. You can check using the strong triangle inequality that all three things are open. Obviously these are disjoint, and so the closed disk is a disjoint union of the open disk and the rim, and you don't want that. You want the closed disk to be connected. So this is somehow caused by the fact there are too many locally analytic functions, which causes this connection. And so what Tate did in the 1950s, 60s, he managed to produce a good category of p-adic spaces called the rigid analytic spaces in the following way. So he said, let's not work with certain local analytic functions, work with a much smaller collection of functions, and throw away some of the open sets as well, and also disallow some open coverings. So the price you pay is that you have to work with a very mild version of a graphical topology, but that's just there to make it sound much more scary than it really is. It's just basically p-adic geometry done right. Which kind of functions did Tate work with? They're the so-called rigid analytic functions. The prototype of such a function space is the set of power series in one variable which converge on the entire closed disk. And you can check very quickly that you can characterize those functions as precisely those power series with the property that the coefficients go to 0 p-adic. And this is a very simple condition in the p-adic world. Over the real numbers, it's much more complicated. Okay. So here's the basics of the theory of rigid analytic spaces. First, the end-state algebra is what you get when you consider power series like we had on the previous slide. Say with n variables, and you throw in the condition that the coefficients have to go to 0 p-adically. And you denote that by k with angle brackets in the variables inside. So this turns out to be a Noetherian algebra. Every ideal is closed, and it's got many algebraic properties similar to a finely generated algebra over the ground field K. And so what Tate did was he said, well, let's consider factor algebras of Tate algebras, called affinoid algebras, and let's consider them as function spaces on the underlying geometric objects, and they're the so-called affinoid varieties. By definition, an affinoid variety is just the maximal ideal spectrum of some such Tate affinoid algebra. So if you like, it's, well, let's just consider this remark first. If you have an affinoid variety, then you can think of the algebra A that produces it as a space of functions on that variety. So by definition, the variety is a set of maximal ideals. Given a function, you can take it mod M, and that will produce an element of the residue field, which by structure theorem is a finite field extension of the ground field K, and so it's some kind of generalized function defined on the function space. And the rigid analytic functions on this X is by definition A again. The basic example is that you can actually recover the n-dimensional polydisk, so just the n-fold product of the disk in one dimension, from the maximal ideal spectrum of this particular algebra.
So your K, can you remind what kind of field your K is?
So K is a complete subfield of the field complex numbers. So it could be discretely valued. I'm not going to be too fussy about that. Some non-Archimedean field. So this is all non-Archimedean.
Basically, no restriction.
Okay. Right, so I've told you what the spaces are in this category of rigid spaces. Now let's talk about the topology. So like in algebraic geometry, you can, if you have an affine scheme, then the Zariski topology in that scheme is given by taking arbitrary unions of basic open subsets, which are just the points where a single function f doesn't vanish. And so what Tate did was he introduced a similar kind of topology on an arbitrary affinoid variety by taking these kind of subsets. They're defined now not by not vanishing of functions, but instead of inequalities given by norms. So note that if I have an element f in that algebra that I started with, then each fi of x is an element of residue field, which is a finite extension of the ground field, and it carries a unique extension of a norm on K. And so this makes sense. This is a real number, and I can talk about this inequality. Okay. So this is some kind of analog of a basic open set G of f in algebraic geometry. And morally speaking, these affinoids, rational subdomains, form a basis for the topology on a rigid space. So it turns out that every rational subdomain of an affinoid variety is again affinoid. You can represent it in this way. Here are some examples to bear in mind. So for example, from the first slide I had the unit circle. It was defined by this equality of norms. So I can also define it by taking this particular algebra. So I take algebra in two variables x and y, and both relation x, y equals 1, and I get kx from 1 for x. I take its maximal ideal spectrum, then I recover this rim. I can also get smaller closed disks and bigger closed disks by varying things. Okay, so you have basically closed disks and rims and things like that in this geometry. So I'm not going to give you the actual definition of a topology because it's a graphic topology and it's a bit complicated. As I said, you throw away, you don't allow arbitrary unions of unrational subdomains. You only allow certain admissible ones, and then you only allow kind of locally finite coverings, and that kind of compactifies the space in a clever way. So you throw away certain coverings of open sets by other open sets. Okay, so that's the topology on affinoid varieties. What's the definition of a general rigid analytic space? Well, what Tate did was he proved that this functor, which, well, given an affinoid variety as a maximal ideal spectrum of one of these Tate algebras, which assigns to that space the algebra you started with, OX, that turns out to be a sheaf in this graphic topology. And that's a good thing because it means you can glue aphanode varieties to form general spaces using elements of this function space to glue. Okay. So let's see some more examples. This time not aphanoids. No, aphanoids are kind of balls in affine n space, maybe, or closed subsets of affine n space. Whenever you have an algebraic variety, so some scheme X locally affine type of K, some algebraic gadget, you can analytify it and get a rigid analytic space. How do you do that? Well, let's take the most basic example. Let's take the affine line. Let's assume for simplicity that K is algebraically closed. As a set, the identification is still K, but I told you that rigid analytic spaces were obtained by gluing together aphanoid varieties, so I have to tell you the gluing, because certainly this guy is not aphanoid. And so one way of presenting it as a rigid space is to consider the field K as an increasing union of a sequence of balls of increasing radius. Each ball is an aphanoid variety, and this turns out to be a nice covering. It's admissible. If you like to think about these things algebraically, you can, well, to this increasing sequence of balls, you can consider the corresponding space of functions, spaces of functions, and you get a tower of aphanoid algebras. Restricted power series in X, and then restricted power series in Px. This is a stronger convergence condition on the power series if you rewrite it to the power series in X. And this is even stronger, and so on. Obviously, the polynomial ring in one variable over K is contained in the intersection of these guys, but you do get other things as well. And so the intersection of this tower turns out to be the ring of entire analytic functions on the whole plane. Here's another example of a non-aphanoid. You can also have the open disk. This is not aphanoid, but you can cover it. You can approximate the open disk by a countable increasing family of closed disks of some radius. Well, let's just, for convenience, pick this particular sequence of real numbers converging to 1 from below. You can define these things using the language I explained. These are aphanoids, and this is a nice covering.
So what makes it admissible?
Well, whenever you have an aphanoid subset of it, the restriction of such a covering has a finite subcover.
Finite what?
Finite subcover. If you have something already compact inside and you restrict the covering, it's already. And then, well, you might object, well, okay, if you've got the open disks in the sphere and the rim as well, haven't you contradicted the fact that the closed disk is supposed to be connected morally? Well, no. If you look at the definition of admissible covering, it turns out that this covering is not admissible. Okay. I don't want to go into much detail. This is sort of classical rigid spaces. It somehow reconnects the totally disconnected closed unit disk. Okay. Right, so now we'll talk about this is joint work of Sam Wadsley, Cambridge. I'm interested in D modules and applications of the theory of D modules to representation theory. So I would like to associate to every, say, smooth rigid analytic space a good ring of differential operators, D of X. Well, what do I mean by that? Why not just do the obvious thing? Well, you can. If you have a smooth rigid analytic space, you can take, there's a canonical construction of just taking algebraic differential operators on that space. It's generated by functions and derivations, because I'm working over a field K of characteristic 0. There are no problems with differential operators in characteristic B yet. So this is a perfectly good thing to do. But of course, the answer to this question always is, well, it depends on what you want to do. So for my purposes, this ring is kind of asymmetric. It's got analytic elements in the functions, in the function direction, and only polynomials in the differential operator direction. So I don't like that. So let's search for something else. Well, why not just make x and del symmetric? So consider the second Tate algebra, kxy, restricted power series in two variables, commutative. Now I'm just going to, by brute force, define a new multiplication on it, star, which satisfies this relation. So I'm not going to actually give a definition here because it will come later, the formal definition, but the theorem is, the fact is you can easily do this. You can define, you can quantize this two-dimensional function algebra into a non-commutative ring. We call it the first Tate file algebra because it's very much like a real algebra from differential operator theory, differential operators, polynomial differential operators on the line, but on the other hand, it looks like the space of rigid analytic functions on a two-dimensional polydisk. So why not try that? Well, there's a problem with this construction. I would like this ring with differential operators to be well behaved. So I would like it to have lots of nice properties similar to the classical theory of D modules on algebraic varieties and complex analytic spaces. So if I just take the Tate file algebra, it's not functorial. So inside the closed disk, you have a disk of smaller radius 1 over p, say. And abstractly, the algebras of functions on these two disks are isomorphic. You can just sort of rescale. When you rescale, however, the base direction, you rescale the cotangent direction in the other direction. And so and there is no conversion path that way. So what to do? So instead, why not quantize the entire cotangent model? So the second Tate algebra kxy is rigid analytic functions on a two-dimensional polydisk. Instead, let's look at rigid analytic functions on the vertical strip. So take a one-dimensional polydisk and take the product of it with the whole affine line in the cotangent direction. You can do that, basically. So this is the main idea. You can present the cotangent bundle of the closed disk as an infinite union of, well, these are polydisks, but their vertical radius is getting stretched as n increases. You can just quantize each one of these algebras naively, and you can rewrite the elements of each algebra in a certain power series in del with coefficients in Tate algebra kx, satisfying a particular convergence condition. It's quite easy. And you think of it as some kind of rigid analytic quantization of this stretched polydisk in the cotangent model. And so this turns out to work quite well, actually. So on the closed disk, which is defined d of x to be the intersection of all these algebras, form a nice nested family. You can take the intersection. It's going to contain, obviously, the rigid analytic functions on the closed disk x and polynomials in del. So it's some kind of completion of the first algebra stuff. And it's now, well, still, you might argue it's still not very symmetric, but that's okay. If I really want to be symmetric on the line, I could now stretch it in the base direction as well. And the theory that we develop actually allows for that. And then you get an algebra which really does allow some kind of formal Fourier transform between x and d by dx. So I should probably remark that as sections, the elements of this algebra can be written as certain power series, so they're rapidly decreasing power series in del, coefficients in kx, satisfying a very strong convergence condition. And it's quite easy to see that when you rewrite them like this, because this condition holds for all n, fiddling around with x doesn't change anything in this condition. And so you get a nice restriction map, and this gives you a functor, turns out. Right, so I would like now to present the general definition of this sheaf Dhat on arbitrary smooth rigid analytic spaces. Morally, it should be possible to do it using some kind of quantization technique, probably Fedosov, maybe something more general, actually quantize properly aphenoid subsets of the cotangent bundle. But we have certain applications in mind to representation theory, and it turns out that a more elementary construction will just do the trick just fine. And so the construction is to take the enveloping algebras of something called Lie-Reinhardt algebras, or KR Lie algebras. Okay, so you should think of this as a generalization of a Lie algebra. So it's some kind of Lie algebra which might not be finite dimensional over the ground ring. So what is a KR Lie algebra? It's a very general object. So you start off with a homomorphism of commutative rings, K to R. K is a ground ring, no longer a field. And R might be some function algebra. Okay, so a KR Lie algebra is, on the one hand, a Lie algebra of the ground field and an R module. It acts by derivations, K linear derivations, on the bigger ring R, and you have this condition. Well, the bracket on L and the action of L and R are compatible in this way. And that's what a K, R Lie algebra or a Lie-Reinhardt algebra is. Okay, well, what you can do with this gadget is you can take its universal enveloping. So this is a more general construction than just taking the universal enveloping algebra of a Lie algebra field. So it's basically generated by R and L as an associative unital K algebra satisfying natural relations. It has a nice universal property, which I shan't bother to spell out. These are the main two examples. So if your two rings in the start of this construction were equal, if R was K, and the anchor map was 0, there's no action, then this is just the usual enveloping algebra of the Lie algebra L. L could be infinite dimensional. The other interesting example is when, for example, X is some smooth variety. Let's say that the ground field K is of characteristic 0. Take R to be the ring of regular functions on X, and take L to be the Lie algebra of K linear derivations of this function algebra. So then the anchor map is just the identity map, satisfying this trivially. And what you get then is you recover the ring of algebraic differential operators on X in this way. So this is some kind of general construction which spits out the universal enveloping algebra in the case of a Lie algebra, and the differential operators in the case where the ring R and the anchor map are not trivial. It's surprising that this construction isn't more widely known, actually, I find. Some people think it's sort of obvious. Some people do use it all the time, but if you haven't seen this before, it's very natural and very well behaved and very general and works with great generality. Anyway, so this is some kind of quantization construction. Some more properties of U of L. It's always filtered. You can take the associated gradient, and then you get the symmetric algebra in good cases. So you can think of it as a quantization of the spectrum of the symmetric algebra of L. That's great. Right, so now what is our general Dhat? Let's start with a smooth aphenoid variety. It has its associated ring of rigid analytic functions. Now, this always has a canonical spectral norm defined in this way. And then you can write down the unit balls both inside the function algebra of X and in the ground field. So this is just the ring of integers if K was QP. Now, let's take the tangent vectors over X, the derivations of O of X. This is naturally a big K, OX Lie algebra, as I explained in the last line. So I can restrict it to the power bounded elements. can view this guy as a OX circle, a K circle, OX circle, Lie algebra. And I look at lattices, which are by definition sub-objects, which are finitely generated modules over this integral structure, and which span Gx as a vector space. So for every such lattice, I can then p-adically complete it and invert P. This is a Banach space completion. And having done that, I take the inverse limit of all possible lattices. So it's not dependent on any choice of anything at all. And so the notation, I mean, there are too many hats from the subject. This hat definitely depends on the choice of L. If you vary L, you get a different kind of topology on U of L. So, well, this is a flattened hat. So just to reassure you that everything's okay, let's reconsider the example I had before. Just take the closed unit disk inside the affine line. This unit ball, the algebra of power-bounded elements, is basically a restricted power series with integral coefficients. And then you can take the free K circle X module generated by P and Del. This is a subset of all vector fields. You can take this developing algebra, and then you get something generated by this ring and basically P to the and L, and then when you p-adically complete invert P, you recover, well, this is the formal definition of what I had before. Okay, so this is a scientific way of sort of making X and Y non-commutative and satisfy the relation Yx minus Xy is 1. And we get what we had before.
So you envelop an algebra consists of polynomial expression in
Yes.
the affinoid. So in which step did you get infinite series?
Yeah. I take the inverse of the p-adic completion.
Yes, I see. Okay.
So here are some theorems. We can prove that Tate's theorem holds for this Dhat. It's local. It's got no higher homology for any finite covering of an affinoid by rational subdomains. That's enough for Tate geometry. And this property is what allows us to extend Dhat to a computable sheaf on every originatic space. I mean, the functionality was already enough to just extend it formally, take the sheafification of the functor. But if I did that, then I wouldn't be able to compute local sections. And because we have this theorem, it's okay. I could do that and I would cover what I had before. So if you like, this theorem tells us how to compute local sections of Dhat over an affinoid. Now, I want to do some D modules, Dhat modules. Well, in classical theory of D modules, you nearly, in the theory of algebraic D modules over an algebraic variety, you nearly always work with D modules which are quasi-coherent as O modules. That's the fundamental category. And frequently you work with a smaller subcategory of those D modules which are locally finitely generated, the coherent D modules. And the reason you get good behavior in this case is because basically locally the algebra of differential operators with polynomial coefficients is Noetherian. And finitely generated modules have good properties. Now unfortunately, this guy is a bit too big to be Noetherian. It's not even coherent, so you can't just fudge and work with coherent modules. As soon as X is an affine space of dimension of these two would leave. Fortunately, there is a way out of this in a very natural way. This is a technique introduced recently by Schneider and Tatterbaum. They proved that Dhat of X is what's called a Frechet-Stein algebra. So I will explain this because it's important. What is a Frechet-Stein algebra? Well, it's an inverse limit of a tower of Noetherian Banach algebras with an extra condition, you require that each AN minus 1 is flat as an AN module. So think of, again, the covering of the affine line by an increasing sequence of balls. It corresponds to a descending chain of algebras, and it turns out in this case, well, restriction of functions should be flat, right? It should be an exact function. So this is what this flat condition is. And then, given a Fisher-Stein algebra, you can define a very nice, very well-behaved category called co-admissible A modules, which is corresponding, well, it's an A module. It must be of the form of an inverse limit of a tower of AN modules, where each Mn is finally generated, and for small values of n, Mn is determined by what happens at infinity. Okay, so think of a coherent sheaf everywhere on the affine line. Every finely presented module is co-admissible. This category is actually abelian. That's very nice. So you view it as a false category of the category modules. Okay, so that's what co-admissible modules are. C of x is the category of co-admissible Dhat modules. Dhat of x modules, because we can prove this is Fisher-Stein. And then if you take a random rigid analytic space, you pick some random covering, and then we can prove that if you glue the co-admissible Dhat of xi modules, and this doesn't depend on the covering, so Dhat modules form a stack on the rigid space. And morally, a co-admissible Dhat module on X should be thought of as a coherent sheaf on some kind of non-commutative version of a cotangent module. Okay, so here's a theorem about Dhat. You can talk about support for a co-admissible Dhat module just in this way. You just look at the locus of points in X where there is a neighborhood where the sheaf vanishes and take the complement. So just look at the zero set of the sheaf and take the complement of that set, call that the support, and then we'll have a precise analog of Cashmarov's equivalence of categories. So whenever you have a closed, smooth subvariety of something smooth, then Dhat modules on Y with support contained in X are canonically equivalent to Dhat modules on X. For example, take the, this would be a Y probably, take the big space to be the closed disk, and you could take the point 0 inside the closed disk. Now, co-admissible Dhat modules on a point are just finite dimensional vector spaces. That's a nice small category. And so here's something that corresponds to a one-dimensional skyscraper sheaf support at 0, so it's some kind of delta function. Okay, so that's basic theory of Dhat. Now I'd like to talk about some applications. Why are we doing this? So, well, it's all well and good to write down nice results in analogy with existing ones. We're hoping that there will be applications to representation theory of p-adic groups. Here's a kind of motivation statement from number theory. So one thing number theorists are interested in is they try to find some kind of bijection, some kind of correspondence between, on the one hand, representations of a Galois group, the Galois side, and on the other hand, representations of a reductive Lie group, on the other hand. So on the reductive Lie group side, you have automorphic forms, and on the Galois side, you have Galois representations. And so this is a particular instance of such a correspondence called the p-adic local Langdon's correspondence for a particular p-adic Lie group, GL2 of QP. So it looks a bit random if you haven't seen it before, but it's quite a powerful statement. So basically, this is the a category of very nice, well-behaved representations of this particular p-adic Lie group. And this is a technical condition. They're admissible, that's important. They're irreducible, so simple objects. And they're unitary Banach space representations with continuous action of GL to QP. So you can conceive of such a collection, and this turns out to be in the canonical bijection with two-dimensional absolutely reducible representations of the absolute Galois group. So, if you like, the p-adic representation theory of this particular p-adic Lie group, this particular category, is explained by some deep number theory. So the functor, well, this actually bijection comes from the equivalence of categories. It's quite non-trivial, and it has very interesting consequences for actual problems in number theory, such as the Fontaine matrix. Now, one problem about this theorem is that it only works for this group at the moment. No other p-adic Lie group. Only GL2 QP. You can't even change QP to a finite extension, and certainly you can't change GL2 to GL3 or something with people trying, but it's kind of a very complicated p-adic thing. How does it generalize to other groups? Well, let me tell you more about this category here, very briefly. So now K will be a finite extension of QP, and G will be a p-adic Lie group, so some closed in the p-adic topology subgroup of GL and K. And I want to talk about admissible representations. I think I will give a sketch definition in the next slide. So this is some kind of finiteness condition on categories of representations. And there are two kinds. First of all, you have Banach space representations, and then you have local analytic ones. This category is strictly bigger than this one. And in theory of p-adic representations of p-adic groups, p-adic Lie groups, you try to sort of understand these categories. So you might try to understand the classifying or reducible representations. Well, this is way too hard, really, because every smooth representation, in the usual sense of smooth representation of p-adic groups, is actually locally analytic. Smooth means that the orbit function is a smooth function, locally constant function of the group, and local analytic means that given any vector in the representation, the orbit function is locally analytic on the group. So everything smooth is everything locally constant is locally analytic, so this category contains all the classical smooth representations of your p-adic group that is used to formulate, for example, the local Langlands conjectures for GLN.
When you say local analytic, it doesn't mean rigid.
It doesn't, correct. It means local analytic in the naive sense. Nonetheless, there is a very nice theory of both Banach space and local analytic representations. Let me briefly sketch these definitions. So these are all continuous representations, and by definition, they are admissible if and only if the restriction to compact open subgroups of the group are admissible. So the admissibility condition is completely determined by the way compact open subgroups act on the given continuous representation. So to put another way, you can think of an admissible representation of a big non-compact p-adic Lie group such as GL and QP as an admissible representation of a compact group such as GL and ZP, which extends as an abstract module, abstract representation to the bigger group. Okay? So let's just talk about compact groups for now. Let's consider admissible representations of compact groups. Here are the definitions. So a Banach, admissible Banach, is some Banach space continuous representation of V such that the strong dual, I'm not going to have time to talk about the topologies involved, is a finitely general module over the algebra of continuous distributions, also known as the Iwasawa algebra of the group KG. This guy turns out to be a nice Noetherian algebra, actually, which is very important. And then it's local analytic, same definition, but you change continuous distributions to local analytic ones. Don't worry if this seems completely unfamiliar. Just think of them as different completions of the abstract group ring KG. So we just take the abstract group ring of G with coefficient with K. That's obviously a stupid thing to do because you're forgetting the group topology on G. So as I said before, there is a way to pass from Banach space reps to local analytic ones. It's called taking local analytic vectors. So you can think of the Banach ones as sitting inside local analytic ones. So let's focus on admissible local analytic So as you saw in the previous slide, what is an admissible local analytic thing? It's something which is dual to a co-admissible module over DGK. So I haven't told you, but it's true that DGK is actually Frechet-Stein when G is compact. So it's a kind of object similar to what we had before. It's an inverse limit of a tau of an Noetherian Banach algebra with flat transition maps. And so I can talk about co-admissible modules. And admissible is basically morally dual to co-admissible. That's the definition of admissible. Right, so now what does this DGK, the representing object, look like? Well, this guy, the Osaka algebra, is really small. It's got no center at all apart from scalars. But the local analytic distributions are a bit bigger. In particular, they contain the enveloping algebra of the Lie algebra. Therefore, they contain the center, which remains central in the big ring. And, well, as the enveloping algebra is kind of non-commutative polynomials and a basis for the Lie algebra, think of it as an algebraic quantization of functions in the dual. So you have this embedding of the enveloping algebra inside this locally analytic distribution algebra, and you can ask, well, what about the topology on U of G induced from that on DGK? What is closure of U of G inside DGK? Turns out to be rapidly decreasing non-commutative formal power series in any basis for the Lie algebra. So a similar kind of object we had before in the section on Dhat modules.
When you say analytic distribution, do you mean hyperfunctions?
You can think of them like that. They're linear functionals on the space of local analytic functions. And with certain topologies. So now if we forget about the group theory again, so you can just talk about this particular completion. Some people call it the Arens-Michael envelope. Doesn't depend on the choice of G. Turns out to be Frechet-Stein. And, well, beforehand, U of G was an algebraic quantization of the dual space of G. And this is a rigid analytic quantization, morally. And so one of our main results is that if we're interested in irreducible objects, you can ask, how does the center act? And we can prove that every simple co-admissible U-hat module has an infinitesimal central character, meaning that the center of the enveloping algebra acts through finite dimensional space, just like in classical theory. And so if you're interested in studying irreducible objects, you might as well factor out by these centrally generated ideals, and you end up with a smaller algebra. It's still a completion of some quotient of U of G. What can we say about this algebra? So this is where D-hat comes in. We can prove that co-admissible U-hat modules with trivial infinitesimal character are equivalent to co-admissible D-hat modules on the flag variety. This is an exact analog of Beilinson-Bernstein localization theorem for D-hat. And you can localize these things to the flag variety. But then the price you pay is that you have to talk about D-hat. Well, so what? Well, here's an application. So remember we had Kashiwara's theorem. Kashiwara's theorem said that if you have some D-hat module supported on a closed analytic subspace of your rigid space, then it comes from a co-admissible module on that space. I'll put another way, if you have something co-admissible supported on co-admissible module over Y, on Y, you can push it forward into the big space. So take M, which is some co-admissible D-hat module living on Y. So Y is just some random subvariety of the flag variety. It could be a point if you like. Take, for simplicity, maybe a finite dimensional X space sitting on it. You push it forward, take global sections, and this spits out a big collection of irreducible objects in the co-admissible category. Right, I'm probably out of time, so here's a list of things we're going to do in the future. If you have questions. today's aspect. Thank you very much.
We have 2 minutes for questions.
On the previous slide, two back. With
Go
B.
back. I can't go back.
In B.
This one?
Here, yes. B. What is B? It's
B
quotient
is
by
flag
block.
variety. So you take the Lie algebra,
But there are two flag varieties.
the
Which one?
full flag variety.
Which?
The full flag variety, take the
So what-
associated simply connected algebraic group, take a Borel subgroup,
So it's
and what have I?
It's not parahoric or something like this. But by parabolic, not parahoric.
Parabolic. Yes.
Yes, at the back.
So what can you say that, I mean, in your future directions, you mentioned something about Riemann Hilbert.
Well,
Is there anything you can say about that now?
there's some work by Scholze published in the last 2 years on integral connections and Biederam local systems. So that's probably got something to do with it. I mean, the main problem is that the topology of a rigid analytic space is still highly complicated. You can't really draw past maybe Konstantin-Ardakov space or something, but even then it's very hard to understand. It's certainly very different to the case of complex manifold where they're locally simply connected. And so you have already in the case of just integral connections, so D modules with, which are coherent as A modules, it's very subtle. But the theory we have, I think, will extend to Berkovich spaces, Adic spaces, and then perfectoid spaces, if necessary, if that's the right direction. We haven't really had time to think about it.
Okay, that's all we've got time for. The IMU committee that asked me to present Konstantin with this gift from them. Thank you. Congratulations. We'll restart at 5:10.